This is lesson 6.4, and the topic today is called partial fractions, and the usage of partial fractions in doing mixed integration. Yes, you hear the word mixed. You're going to see a whole bunch of different integration techniques put together. This lesson is important, especially for the next lesson, as the next lesson involves partial fractions. You've seen partial fractions before. It's like me doing this. If I said, hey, I've got 1/3, I got to add to that 1/4, you can combine that together to give you 7/12. Well, the idea today is if I give you 7/12, can you go back and find the two partial fractions that make it up? So, it says we have often simplified expressions like this. So these are rational expressions now. 1 over x minus 4 minus 1 over x minus 3. How do we do that? Well, you get the common denominator, and then you combine the two fractions into one. So once again, our goal today is to reverse the process. And we want to reverse the process because sometimes splitting a single fraction into two separate, simpler fractions make it much easier for us to integrate. So, example number 1. If I look at this lovely integral, I should get scared, because if I want to let u equals to, and please don't write this down, x squared minus 7x plus 12, thinking I can use substitution 2x minus 7, I am wrong, because I can't make a good substitution, so I'm stuck. You could try some of the other techniques, like inverse trig, which we learned 2 lessons ago, or even integration by parts, but you're still going to get stuck. So let me introduce you another way here. Can you see how the denominator can be factored? I hope you can factor this easily into x minus 3 and x minus 4. Say yes. Good. So here's the plan. The plan is for us to find two fractions, one with a denominator of x minus 3 and another with the denominator of x minus 4. I don't know what the numerators are, so let me just call them capital A and capital B. But if I add them together, I should be able to come up with the fraction 1 over x squared minus 7x plus 12. The goal now is, how do we do it? Well, in order to equate fractions, you have to have the common denominator. So if I have the common denominator, what I need to do is make the first fraction here. I guess I'm missing an x minus 4, so I'll multiply the top by x minus 4. The middle fraction, I'm missing an x minus 3. X minus 3, I guess, goes on top. And on the right hand side, I'm not missing anything, because that's just x minus 3, x minus 4, so I'm good. Of course, once the denominators are the same, we can equate the numerator. So therefore, what I have here is a times x minus 4 plus b times x minus 3 is equal to 1. Now, your goal here is to solve for a and b. How can you do this? Well, there are a few ways. You can go ahead and multiply this out and equate all the coefficients of the terms. Or there's a more quicker and probably more efficient way. This is an equation. So for an equation to be an equation, the left side must equal to the right side for whatever values of x you choose. So if I were to choose x being equal to 4, notice what happens. I get a multiplied by 4 minus 4, which is 0. And b multiplied by 4 minus 3, which is 1. And this equals to 1. Leading me to know that b equals to 1. So similarly, I can choose another value of x, and guess what I'm going to choose? If you said 3, you're correct. And look what happens here. It's a times 3 minus 4, which is negative 1, plus, in this case, b times 0, and that equals to 1. So that leads me to know that a equals negative 1. So why are we doing all this? Well, what you've just told me is this. Therefore, okay, remember that integral we started with? Yeah, that one from the top. I can now rewrite that as two partial fractions. It's the same thing as this. I know now the a value is -1, so -1 over x minus 3, plus b, which is 1 over x minus 4. And this is now my integral. Why is this so much nicer? I hope that you remember that this integral is just the natural log of x minus 3, but wait, there's a negative front, right? And I hope you remember that this is just the natural log of x minus 4. And lo and behold, with another plus c, I am done. And this is your integral. The beauty of the partial fractions here, especially when they're linear fractions or linear factors in the denominator, is that the integral is just equal to natural log. Remember? The integral of 1 over x is just natural log of the absolute value of x plus c. Okay, so I just did example number 1. Example 2 is very similar. I'd like you to try this out now yourself. Okay? Try it, then come back. Let's take a look together. Factor, factor, factor. So let's rewrite this as a over x minus 3 plus b. Should put an equal sign there, not really equal. B over x plus 1 equals to 5x minus 3 over x squared minus 2x minus 3. Common denominator, all that business. I'm just going to skip a step here too. Just going to go straight to equating the numerators. Here we go. Once again, I can use that trick to understand that no matter what value of x I plug in here, the left side must equal to the right side. So plugging in, let's say x equals to -1, I get a times 0. B, let's see, that's -4. And this, -5 minus 3, that's -8. -4b equals -8. Hello, b must equal to 2. Nice. Do the same thing now if x equals to 3. A times 4 plus b times 0. 5 times 3 is 15, minus 3 is 12. 4a equals to 12. A equals to positive 3. And so, now we're ready to rewrite this integral as the integral of two linear rational expressions. Well, not linear rational expressions with a linear denominator. Here we go. A was 3, so 3 over x minus 3 plus b, which is 2 over x plus 1. And this is all being integrated. Once again, just go ahead and use natural logs. The 3 is a constant, we take it out. The 2 is a constant, we take it out. And don't forget the lovely plus c. If that's what you got, give yourself a pat on the back. Cool. Turn the page. Now, let's try another one. Okay? If you're going to go ahead and once again factor, that is cool. And you can go ahead and try to do the partial fraction thingamabobber. That is cool, but I'd say you're wasting your time. Remember, my suggestion always is not to try these weird techniques, but to try something simple first. And if you could see that this was u, and your denominator could be equal to u, and if I asked you to take the derivative, do you see where I'm going here, dear friends? This just becomes a regular substitution, a u substitution. So don't get confused or freaking out that every single question has to be done by partial fractions if they have a denominator that can be factored. I would always suggest you always try substitution first. Look how much easier this one is. guess it would be natural log of u. And then I'll just replace u with x squared minus 2x minus 3 plus c. Ta-da. Okay? So always make a note. Try substitution first. Excuse me. How about number 4? Another weird one here. This one, notice the numerator's degree is 1 higher than the denominator's degree. And we had an example like this 2 sections ago in the inverse trig video. Do you remember how we dealt with this? If you said long division, I think you're right. So, take the opportunity here to do some long division. And that helps because, well, I hope you'll see in a second. But as I do this long division, you should be asking yourself, x squared times what gives you x cubed? You said x, that's great. So x times x squared is x cubed. X times x is x squared minus 2x. Of course, you're subtracting all this, so x cubes disappear. 0 minus 1 is just negative x squared. Negative x minus negative 2, that's positive 2x minus x, that's plus x. And then I'm going to drop down to 2 and ask yourself x squared times what gives you negative x squared? It's negative 1. And if we subtract here, you'll get 2x. So what did you just say? You just said the following. I can now rewrite this integral as the integral of the quotient x minus 1 plus the remainder, which is 2x all over x squared plus x minus 2. And I'm going to have to integrate this. Okay. Now, integrating the first 2 terms here, that's easy. The difficult part is integrating this fraction. And I could try to use substitution, but if you did, I think you might run into a roadblock. du dx is equal to 2x plus 1, and I don't have a plus 1 up there, so boo-hoo. So if substitution doesn't work, and you see how you can factor this, then you should be thinking partial fractions. Okay? So go ahead, let's see if you can use partial fractions to rewrite this rational expression into 2 hopefully linear factors, and then you can just use natural log to solve. Try it on your own. So a over x plus 2 nasty, eh? This one, combining all the different things you've learned. Long division. And now partial fractions. If you didn't think pre-calc 12 was important, I hope you are thinking otherwise now. Skipping a few steps here, just plugged in 1. Uh-oh, I see fractions, but nonetheless still okay. What should I plug in now? Negative 2, so that's negative 3 plus b times 0, negative 4, a equals to 4/3. Okay, running out of space, but nonetheless doable. So let me just rewrite this integral down here. Once again, it's the integral of x minus 1, and now that 2x over x squared plus x minus 2 is now the partial fraction a, which is 4/3 over x plus 2, plus b, which is 2/3 over x minus 1, and this is all d with the dx. So now just go ahead and integrate. The integral of x is just x squared over 2. The integral of 1 is minus x. Here's our fraction 4/3 and natural log of x plus 2. along with another 2/3, the natural log of x minus 1. And once again, don't forget plus c. There you go. It probably doesn't get much harder than that. Now the hard part with integration is they all kind of look the same. In our next example, I've got 4 what I call look-alike integrals. They look the same, but each requires you to use different integration techniques. So, I want to see if you can just try to apply those different integration techniques now to see if you can integrate a, b, c, d in example number 5. If it doesn't help for a, perhaps writing it like this this is 1 plus x squared, and I hope you remember from 2 lessons ago, this is the inverse tangent function. And it's a linear factor like this in the denominator. I hope you also remember from last chapter that that's just the natural log of 1 plus x. Notice in this one, I do have a 1 plus x squared in the denominator. This is where I think I'd use substitution, because du dx is 2x, and therefore du is equal to 2x dx. I can divide both sides by 2x, and you'll see that this becomes 1/2 1 over u du. And so when I integrate that, I get the 1/2, the natural log of 1 plus x squared plus c. Yeah? And if you're thinking about this last one, may I suggest you write it like this. And if I integrate using powers, even though this is like a u substitution, I guess I could use u substitution if you really wanted me to. Du dx equals to 1, so du equals dx. So this actually becomes u to the negative 2 du. I can integrate that using power rule. U to the negative 1 over negative 1. I will then replace back u. So notice I just get this plus c. And you see how they all look or not the same, but similar, but they give you completely different integrals. And this is where you just need to know the different types and do some practice to identify which you should use. Okay, 2 more here. Number 6. Integrate these 2 lookalikes. Alright? I won't actually do these for you, but I will give you a hint. They're both just substitution. Okay? Nothing involved with partial fractions or whatnot. And my suggestion when it's substitution is this. Perhaps let both of them equal ln x. Alright? I'm going to leave this up to you. You come back and give me the answer while I see you in class. Alright? That's it for partial fractions. See you in class. By the way, do this part well, because you're going to need it for 6.5's lesson.